For this class, we'll look at momentum and impulse. At this point, guys, we've already discussed that momentum is related to Newton's second law, remembering that an object in motion will tend to stay in motion, and an object at rest will tend to stay at rest. And that's summarized by the equation that we already went through. Force net equals mass times acceleration. Now, also remember that acceleration from the first part of the year we looked at was change in velocity over change in time. We could then change our first equation, force net, mass times acceleration, or if acceleration is change in velocity over change in time, we could rewrite it this way. So with mass times change in velocity over time. Now from last class, or last week, we looked at momentum. And we said momentum is mass times change in velocity. Well, you have mass and change in velocity here. So you could substitute in change in momentum, and you would end up with force net is your change in momentum over time. Solving for momentum, we could find that by cross multiplying here, we find that momentum is force net times time. Now that's given a different name. At this point we'll call that impulse. When we're talking about force and the amount of time a force is in contact with an object, that's impulse. Okay, that should become more clear now with this example. Pillow and brick question. A 15 Newton pillow 1 meter above a man, and you have a 15 Newton brick 1 meter above a man. Now both are going to fall. And the question is, which one would you rather be hit with? Looking at both, we see that both would have the same mass and the same weight. They have the same weight, 15 newtons, and remember, you get your weight, mass times acceleration. Acceleration due to gravity is 9.8 meters per second squared. So both are working at 15 newtons. Both are being acted upon by gravity the same. Both must have the same mass. Ignoring air resistance or any friction, both fall at the same velocity. And because of that, they both have the same momentum. The question is, which is better to be hit with? So both falling with the same force, same momentum. So which would you rather be hit with? Now, there must be something more to the question, and it has to be impulse. Obviously, you'd rather be hit with a pillow. Impulse is defined as the product of the unbalanced force or net force and the time that the force is acting on it. And summarized here by this formula. And with the symbol J for impulse. So impulse is force net multiplied by time. From the pillow and brick problem, both objects have the same weight and drop from the same height to hit you on top of the head, and both fall at the same rate. Now we know intuitively that you'd rather be hit with a pillow. It's not going to hurt as much, and the reason being is since a pillow is soft and flexible, strikes your head and begins to settle around it and take the shape of your head before coming to a stop. The pillow takes more time to stop, and we'll say half a second. The brick is very hard and does not give as it hits your head and comes to a stop very quickly. So the difference between the two is that the pillow is in contact with your head a lot longer before it stops than the brick. Think of throwing a ball on top of a rubber bouncer on top of the floor, how much it would bounce, and then taking that same rubber bouncer and throwing it against a mattress. It's going to be in contact with the mattress for a much longer period of time before it stops, so that way it doesn't bounce, as you don't get the recoil back. Whereas if it hits the floor, it's in contact very quickly, the floor doesn't have any give to it, and it bounces much more. It's the same idea here. So the time to stop is different in each case. The 15 Newton feather pillow takes half a second to stop, and the brick at 15 with a mass of 15 newtons takes 0.01 of a second to stop. Sorry, I think that might be a mistake from the earlier. It should be 0.10 seconds to stop. Now, how much force does each have on impact? Since each object has the same mass and velocity, they have the same momentum. And remember, momentum should be an equals, is mass times velocity. That's an equal sign there, guys. If the momentum of both are equal, we consider the impulse of each collision to be equal. Since the impulse in each case is 60 newtons times second, remember, it's impulse. The formula has force times time, so it will be newtons times second. 60 newton seconds. Compare the impact of each. Well, for the pillow, it strikes with 60 newtons of force. The impulse is 60 newtons times second. We don't know the force, but it's in contact for half a second. So solve, just use algebra, divide both sides by 0.05, and it's 120 newtons. For the brick, it's 60 equals, and the force we don't know, but the time is 1/10 of a second. Divide both sides by the 1/10. And you find that you have 600 newtons. So when the brick hits, it delivers more force than the pillow because it takes more time to settle. More of the energy of the fall for the pillow goes to shaping the pillow around your head. It's just in contact for a longer time. So if you can lengthen out the time of an impact, you take the force away. Okay, we'll look at impulse in sports. So we have various pictures here of different impacts. Hockey player, and the bend in the stick. Baseball player here, and notice the bat has very low bend in it. So you should be able to tell now that the puck in this case should have less force delivered to it than the ball. Now the other factor here, before someone starts questioning it, is also the spring action in the stick. Now we don't get into that, but that is a second factor. Tennis racket and the amount of time that the ball will be in contact there. If you look at the hammer, striking the nail, very quick impact, delivering a lot of force. And trampoline. I won't get into this one right now, but there's a video link that gives some explanation of the sweet spot when you're hitting a bat, the best place to hit it and why there's a best place to hit it, and it has to deal with impulse. So if you're interested, you can take a look there. And important points for us here: a short interaction time, or time to stop, equals the larger applied force. So think of here the hammer. It's a short time to stop, quick interaction, more applied force. A longer interaction time, the longer the two surfaces are in contact, the smaller the applied force. So think someone jumping up and down. The longer you're in contact with that trampoline, the less force that's applied to you. And you can think of it this way: which is easier for you to jump on? To jump 10 feet onto a trampoline up and down, or to jump from 10 feet onto concrete? Trampoline's going to be much easier on you. You're in contact with the surface of the trampoline much longer than you will be just hitting the floor. Because the trampoline itself, remember, it's flat, and when you jump on it, it has to take time to curve the canvas. The time it takes to curve that canvas is the time that saves your kneecaps. Because if you were to jump 10 feet on the concrete, I think you'd certainly find a bit of a difference there. Okay, we're going to pause this video here, or stop this one, and we'll get into the part 2 in a moment.